Okay, in this screencast we're going to look at Diophantine equations which are concerned with finding integer solutions to equations. Now we're going to be focusing on linear Diophantine equations. So linear equations you're familiar with. So for example, 2x plus 3y, to pinch from the book, equals 5. Now, there are an infinite number of solutions to this equation, but what we're interested in with Diophantine equations, are there any integer solutions? There may be, there may not be, but there's an infinite number of solutions, and we've done lots of work with linear equations, and typically we've looked at equations such as this, and we've drawn graphs, we've found gradient, and we've looked at drawing the graph of such an equation. Obviously, is a line. So if we graph all the x, y coordinates that satisfy this equation, we have a straight line. But does that straight line go through any integer points? So if we were to concern ourselves with this momentarily, what we're looking at, I've drawn the grid lines on this page just so that I can highlight that point, is that if we were to draw this, we would say we could turn this into a y equals and work out from that the gradient, and in this case it would be minus 2/3 x plus 5/3. So we'd go to 5/3, which is 1 and 2/3, and we'd put a marker down there. In fact, I probably should draw a nicer. Okay, so I've just drawn an xy plane here, and to sketch this particular linear equation here, we've got a 5/3 y-intercept, which is about there, 1 and 2/3. Then it's a minus 2/3 gradient, which means minus 2 rise. So rise of 2 and 3 across. So 1, 2 up, 3 across this, 1, 2, 3. So we're looking at a line that looks a bit like this. And that's fine. Look at all those. This line represents that infinite number of solutions to this equation. However, I re-emphasize the point with the Diophantine equation, we're interested in the integer solutions. So Diophantine equations search for, or is the study of, integer solutions to for linear Diophantine to linear equations. Now, the search for integer solutions to nonlinear equations, you will be familiar with some of these. For instance, if you're looking at such a scenario, c squared equals a squared plus b squared, you'll recognize this as Pythagoras' theorem, and you know that there are many, again, an infinite number of solutions, integer solutions to this, and we've to such an equation, such as 5 squared is equal to 3 squared plus 4 squared. So a equals 3, b equals 4, c equals 5 is 1. And then just doubling will give us 6 squared plus 8 squared is 10 squared. So these are called Pythagorean triads, and there's an infinite number of integer solutions to such a thing. That's not linear, that's a quadratic Diophantine equation. But interestingly, powers of 3 or above, as this is a problem that has challenged mathematicians down the centuries, finding integer solutions to power 3 and above equations. And this is famously known as Fermat's last theorem, in that the proof that there are no solutions, there are no integer solutions to such equations of power 3 or greater. And the proof of that has taken hundreds of centuries to essablish, and actually only very recently a formal proof has been presented to such to Fermat's last theorem. So it's in looking at linear Diophantine equations, we're just interesting to look at the wider picture. But let's get back now to such a thing. Now, okay, so does this straight line go through any corners? Does it go through any integers, integer coefficients, integer coordinates? I beg your pardon. All right. Well, you can perhaps just look at some examples here. Maybe make x equal to 0, y, no, that's not 1, x equals 1, no, x equals 2, 3, 4. Well, actually x equals 4 gives us 8, and we put y equals minus 1. So does 4x equals minus 4 and y equal to minus 1, is that a potential Diophantine equation solution to 8 minus 3 equals 5? So 4 minus 1, x equals 4, 1, 2, 3, 4. So this line should go through 1, 2, 3, 4, minus 1. Should go through this point here. And if I'd drawn this line correctly, then it would have done. And in fact, I might just attempt to do such a thing. So I know it goes through this point, and I know it goes through here on the y-axis at 5/3 or 1 2/3. So it's actually a line that goes through these 2 points, and so that is the point there for minus 1, integer solutions to this equation. That's what Diophantine equations are all about. Okay, so how to find these integer solutions? Well, let's have a look at another equation. Again, I'm pinching from the textbook, and that is, well, actually, the first thing to understand is that the greatest common divisor of if we're looking at this in terms of ax plus by equals c, then, all right, we need the greatest common divisor of our a and our b. Our greatest common divisor needs to also divide our c, and if it does, then we have integer solutions. If it doesn't, we don't. So for instance, our GCD, our greatest common divisor of, in this case, 2 and 3, which is just equal to 1. Now 1 does divide 5, so therefore if what we're looking at here is our greatest common, if these coefficients of a and b, and I'm referring to a and b, I should talk about a, so this is the general Diophantine linear equation, ax plus by, well, it doesn't have to be Diophantine, it's just a general linear equation, equals c, then if my GCD, my greatest common divisor of a and b, divides c, then we have integer solutions. We have integer solutions. We have an infinite number. Have an infinite number of integer solutions. And that's an important point to make. But in order to find that infinite number, well, we need to find 1 initially. And so that's going to be our task as we set out on this path of finding some integer solutions to linear equations. Okay, so our greatest common divisor in this example was 1. And so if my a and b are relatively prime, then we are always going to have solutions to our Diophantine equations. To a Diophantine equation that has a and b as being relatively prime. So that's an interesting side point. Okay, so let's have a look at let's look at an example. Consider the equation. Let's have a look at. I'm just going to have a look at the one that's given to us in the book. So 27x plus 15y is equal to 21. Okay, so consider that, and our first thing is all right, what we want to do is find one solution, one integer solution to this equation. All right, so we want to find one integer solution. If we find one, we can find the rest of them. Okay, well, what we want to do here is let's establish what our GCD of 27 and 15 is. So let's get to work on that. So the GCD, our greatest common divisor of 27 and 15. Now, how do we find our greatest common divisor? If you remember, we can use the Euclidean. Right, using the Euclidean, I should use a capital E because this is a fella's name, Euclid. Using the Euclidean algorithm. All right, using the Euclidean algorithm, we establish that 27 is equal to 15 times 1 plus 12, and then now we establish that 15 is equal to 12 plus 1 times 12 plus 3, and then we get 12 is equal to, well, that's just 4 times 3, and with no remainder. So here is our greatest common divisor of 27 and 15. That's equal to 3. So therefore, working backwards, 3 is equal to 15 minus 12. All right, we've got that. And now, well, that's equal to, I'm moving a step up. 15 is equal to 27 minus 12, and 12 is equal to 27 minus 15. Now, what do we want to get things in? We want to get things in 27s and 15s. So this 12 has to go here. So I've got 27 minus, now the 12 is 27 minus 15. That gives me my 12 minus 27 plus 15 if I lose the brackets there. So if I gather everything now, I've got 27 minus 27 minus 27. So I've got 27 by minus 1, and I've got 15. So I've got positive 15 and a positive 15 here. So I've got two 15s. Okay, so I think I just read that the wrong way around, didn't I? Or the other way around. So it's 15 by 2. And if you look at it, that's minus 27 and 30. That's my 3. That's all good. So so from this, I can therefore determine that that 27 times minus 1 plus 15 by 2 is equal to 3. So therefore, my integer solutions to 27x plus 15y equals plus 15y, excuse my dog, equals 3. I remember 3. I'm going to move to 21 in a minute, but 3 is, I firstly find out my solutions for the greatest common divisor of 27 and 15, and then I work in. All right, 3 are x equals minus 1 and y equals 2. Okay, however, so therefore, for 27x plus 15y equals 21, okay, I'll rewrite that. All right, so I'll rewrite this as, I'll rewrite this step more clearly. Therefore, since 27 by minus 1 plus 15 by not minus 2, positive 2, I'll lift my game here, plus 15. Given that that's equal to 3, we want to solve for 21. So we're multiplying by 7. So all I need to do here is multiply these by 7 and this by 7. So therefore, integer solutions to 27x plus 15y equals 21. All right, remember 21 needs to be a multiple of my greatest common divisor. Are x is equal to minus 7 and y is equal to 14. All right, so there are my integer solutions to this equation here, and that was my task. So the first job was to find one integer solution to this equation. Now what we're going to do next is we're going to find the general solution to this equation. We're going to find all the other infinite solutions. Remember, if the greatest common divisor of AB divides C, then we have an infinite number of solutions, integer solutions. We find one and then we find the rest. But we find that one by firstly working through the greatest common divisor. So we solve this equation equal to its greatest common divisor. Using the Euclidean algorithm, we solve that. Then we simply multiply our solutions for, in this case, 3, multiply them by 7. So we have minus 7 and 14. So that's my one solution there. Okay, now I say, righto, well, if in that case, actually, if I've got 27 by, I can say 27 by minus 7 plus 15 by 14, if that's equal to 21, well, what I can do is actually, to find my next solution, what I'll do, I'll change color here. I can say I can add a 15 here, because what I'm doing is I'm adding a 27 by 15, and I can subtract the 27 by 15 there. Excuse me, I'll just get rid of this dog. Okay, so just to explain that step again, if you look in blue, I've added 15 by 27 and then subtracted the 15 by 27, so I'm still equal to 21. So I've got another solution here. So I've got another solution, another integer solution is, all right, x equals 27. This is my x, remember. So now x equals 8 is a solution. Minus 7 plus 15 is 8. and y equals minus 13 is a solution. And if you check it, 27 times 8 plus 15 by minus 13, that's going to get you 21. But we don't stop there, do we? If you think about it, actually, if I now add another multiple of 15, so I add 30 here, and then another multiple of 27 here, then I'm going to get another integer solution. So here's where my infinite number of integer solutions come from. I can say, therefore, I can say 27 by minus 7 plus 15 by, say, k for some integer k, plus 15 by 14 minus 27k is equal to 21 for k integer, any integer k. So I've now established all my another interruption. Excuse me. So here's our integer solutions now, or our infinite number of integer solutions: minus 7 plus 15k for x, 14 minus 27k for y. However, to keep them as small as possible, we can divide this 15k here by the greatest common divisor 3, and minus 27k divided by the greatest common divisor 3, that's still equal to 21. So actually our integer, therefore, x will equal our general solution, minus 7 plus 15 divided by 3 is 5k, and y will equal 14 minus 27 over 3 is 9k. So there's our general solutions to this linear Diophantine equation. So in general form, well, we can extrapolate and write it in general form. However, I think that's probably the easiest way of doing it. I think writing out your solution in such a format will get you to your general solution. Now, that one example there takes us right through for the first 3 exercises in chapter 4. So I think we can now go from exercise 4a through to 4c, because what 4a will do, it'll work with perhaps the first part of this. 4b brings in the second part, and 4c will then draw on our general solution to our linear Diophantine equations. So it's a 17.5 minute YouTube, nice and long, and I apologise for that. I perhaps could have broken it up a little for you, but I got too into it. And actually, we've just worked through one example. So now there's plenty of material there, and now we just need to go and practice our work. So exercise 4a, starting on from page 43. So that's your task for Monday, and probably Tuesday and Wednesday as well. Okay, I'll see you soon.